So I ran out of space, but basically what I was saying is we're going to call each one of these points something. So we'll call this x1, x2, x3, x4, x5. We can call a x sub 0. And just thinking about how we might actually find this area. So if we use the right hand as the tops of our rectangles, then they would look like this. You might imagine that it doesn't actually matter which side you use if these are getting infinitely narrow, right? Because what you might expect is that the left hand or any point in the middle or the right hand, those approximations might approach each other. But basically what we have now is we have that the area, the total area here, is going to be whatever the width is. So in this case, it's b minus a over 5 times each one of those function values. So that should be f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4 plus f of x sub 5, right? And that should give us the total area. So a lot of times how we could write this, since it's a sum, is to write, whoopsies, that is not a sum symbol. We can write the sum from I equals 1 to 5 of f of x sub I, right? So that is these all added together, and each one of those is multiplied by delta x, where delta x is just that, basically b minus a over 5. In other words, the width, the change in x. So just as a reminder, this means sum up. This means multiply the height by the width. So we're basically summing up a product of heights times width, which should give me basically this area plus this area plus this area plus this area plus this area, or the total area. And so what we can basically think about is really what we want to do is have more and more and more of these. So what we could actually think about wanting is maybe a limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x, where delta x now is the length of our interval over n. So now we can think about, okay, so we've got infinitely many of these, right, as n approaches infinity from 1 to n. So we've got f of x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub million, tons of these, right? And then we're multiplying it by a delta x that's going to 0. So it's this infinite sum of things that are getting infinitely small, and it's that sort of balancing act that makes calculus so beautiful. And thinking about the picture here, I'll just destroy this, is really what we're doing is we're getting all these tiny, tiny little rectangles, right? And the amount that you're then over and underestimating is getting so small, and your widths are getting really tiny. And so you can imagine that as n goes to infinity and you get lots of rectangles, you're actually going to get this sort of perfect approximation of the area. And that's sort of where we're going. Okay, turn the page to some examples. Okay, so here's example 1. Consider this. Use 4 rectangles to find a lower estimate for the area under the curve from x equals 0 to 8. Sketch the approximation on the graph above. So 0 to 8, we've got 4 rectangles. So to find our width, we can do basically 8 minus 0 divided by 4, which is pretty clearly 2. So we want our rectangles to have a width of 2. So I will draw these little lines here. So we've got a width of 2. Then it says find a lower estimate for the area under the curve. So we're going to use the left-hand approximation. We're going to use these as our heights so that we get an underestimate. So that's the area we're going to be writing a sum for, which is an under approximation. So basically we're going to have our width 2 times f of 0, that's the height of the first rectangle, plus f of 2, that's the height of the second, plus f of 4, height of the third, plus f of 6, height of the fourth. Make sure not to go all the way to f of 8, right? Because we only want 4 rectangles and we're using the left-hand side. So I don't know, what is this graph? I don't know exactly what this graph is, but it looks like that is, f of 0 is clearly 2, so it should be 2 times 2 plus f of 2 looks like it could be 4, I guess. We'll just estimate it at 4. F of 4 looks like it's about 5. F of 6 looks like it's about 5.5. So that should be 2 times 6, 11, 16.5, which is 33. So looks like it's about 33. If your estimation isn't exactly that, that's okay. Okay. For the same function, find an upper estimate using 2 rectangles. So sketch the approximation on the graph above. I'd encourage you to pause and try this on your own. But 2 rectangles from 0 to 8, meaning our rectangles are now have a width of 4. They want an upper estimate, so now we're going to use this side to make our rectangles giant. Like this, they're going to overestimate the area under the curve, and it's going to look like that. Okay, so that area should be our width, 4 times f of 4 plus f of 8. Right, we only want 2 rectangles, so let's make sure we just do that. That's going to be 4 times, let's see, f of 4 we decided was 5, and f of 8 it looks like it's about 6. So that should be 4 times 11, which is 44. So it makes sense that our underestimate was 33, our overestimate is 44, so the actual area under that curve is somewhere in between. Okay, here's an example that's more with tabular data. So speedometer readings are given in the table. We've got time, our x values, and speed, our y values. Estimate the distance traveled by the motorcycle during this time period using the velocities at the beginning of the time intervals. So that would be this one, this one, this one, this one, and this one. So basically our width is 12, right? And these are our heights. So basically we're going to say, all right, let's multiply 12, which is the time that we were at each one of these velocities. We weren't actually at 30 feet per second the entire time, but we're estimating, we're using that as an estimation for the velocity we were at for the first 12 seconds. So we'll do 12 times 30, and then 12, so that's this interval, then 12 times 28, then 12 times 25, then 12 times 22, and then 12 times 24. And we'll get some number, feet, because we're multiplying seconds by feet per second. So you can find that number. I'm not going to take the time in the video to compute that in my head, but we could definitely do that. Into the time periods, well, it would just be 12 times 28 plus 25 plus 22 plus 24 plus 27. Again, we really don't, we only want to use, when there are 1, 2, 3, 4, 5, 6 things, we only want to use 5 of the times, because otherwise we're finding an extra interval that we don't want. So there are only 1, 2, 3, 4, 5 intervals, so we only want 5. And again, that's going to give me some answer in feet. Are your estimates in parts A and B upper or lower estimates? So to figure that out, a sketch might be helpful. So this is 12, 24, 36, 48, and 60. So basically it starts at, let's say, 10, 20, 30. So at 0, we're at 30. At 12, we're at 28. At 24, we're at 25. At 36, we're at 22. 48, we're back at 24. 60, we're at 27. So it looks like our velocity is doing something like this. So because it's both increasing and decreasing, it's hard to tell whether our, the first one is looking like this. So it overestimates, it overestimates, it overestimates, then it underestimates, then it underestimates. Looks like it overestimates more than it underestimates. So I would guess that the first one is an over. And the second one, it underestimates, 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 then overestimates, then overestimates. So probably under, because it looks like it underestimates more than it overestimates. But again, it's hard to tell because the velocity both decreases and increases. So coming back to the last example here, hopefully the video will keep playing. But partition, cut up the interval from 0 to 12 into 6 subintervals of equal length, call the equal length delta x, then evaluate the sum from I equals 1 to 6 of j of x sub I times delta x. So these are our heights, and these are our widths for each of the following. So cut 0 to 12 into 6 subintervals of equal length. So that should be 12 minus 0 divided by 6, which is pretty clearly a width of 2. So my first one is there. Second one is there, third one is there, fourth one is there, fifth one is there, sixth one is there. So these are my intervals here. Then it says x sub I be the right endpoint of the ith subinterval. So the right endpoint would be this one. That would have basically an area of 0 because my height is 0. Then I would use this one. Then I would use this one again, so it's going to have a height of 0. Then I would use this right interval. So when you use the right, then when you're drawing your rectangle, you're drawing back over to the left. And then this one. So that's my my first one is basically has a height of 0. Then my second one's got this height. Then I have another height of 0. Then I have this height, and this height. 1, 2, 3, 4, 5, 6 rectangles. So that is going to be 2 times 0 plus negative 3 plus 0 right here plus, that looks like about 3 plus, let's just call that 2, and let's call this, I don't know, 1.8. So that would be 2 times, these are going to cancel out the negative 3 and the 3. In other words, that area is negative, that area is positive, so they basically undo each other. And so then it's going to be 3.8, and 2 times 3.8 is 6 plus 1.6, 7.6. The midpoint of the ith subinterval, interesting. So now instead of using the right or the left hand, we're using the midpoint. So that would be right there, right there, right there, right there, right there, and right there. So this rectangle would look like that. This rectangle would look like that. This one would look like that, 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 and that. So that one's going to be the midpoint there, midpoint there, midpoint, 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 and midpoint. So again, the width is 2, and then basically we'd have to figure out those heights. So it looks like this one is, I don't know, maybe 1.8, and then the next one looks like it's about negative 2.3, and the next one looks like it's about negative 1.8 or something. This one up here looks like it is at about 2.4 or something. And then we've got maybe another 2.4, and finally a 2 or something. 1, 2, 3, 4, 5, 6. Should have 6 heights. And so then that becomes 2 times, well, we're just going to estimate here. Those are gone. This is going to be 0.6 in the positive, so maybe 1.8 plus 2.6. So now we've got 2 times 3, 4.4, which is around 8.8. So you can see we're getting some different estimations here for that area. So that should give you an idea of Riemann sums. Just as a little bit of a summarization, right now we've got right hand, we've got left hand, and we've got midpoint, different ways to choose your heights. You could also do a trapezoidal, but trapezoidal, you know, where you've got some curve and you're cutting it up like so, and then you're basically using trapezoids to estimate like so. Trapezoidal is really finding the right hand and the left hand and averaging them, which should get you a slightly better approximation. So that should give you a good idea for Riemann sums.